Okay, so we all know that gravity keeps our atmosphere from flying away. But have you ever wondered what actually keeps our atmosphere, well, up in the atmosphere? What stops it from crashing down to Earth? Scientists set out to solve a completely different scientific mystery may have just figured out why. Hey Space Cats, I'm Dr. Maggie Lou, and in this week's video, we're talking about what keeps the sky in the sky. So let's begin. As you know, Earth has a gravitational field. It's generated by the Earth's mass, and it governs the force of gravity that pulls objects to the ground. It has a magnetic field produced by the movement of molten iron within the Earth's core, and this extends all the way out to space, protecting the planet from solar wind and cosmic radiation. However, what most people don't know is that the Earth also has an electric field, which is distinct from our magnetic field. The electric field in the atmosphere is primarily due to the differences in the electric potential between the Earth's surface and the ionosphere. The Earth's surface is typically negatively charged, while the ionosphere is positively charged. This difference in electrical potential creates an electric field that extends from the ground up into the atmosphere. Now, since the late 1960s, spacecraft flying over the Earth's poles would detect streams of particles flowing from our atmosphere into space. Scientists called it the polar wind, but no one really knew why or how the particles were actually escaping. Some amount of outflow from our atmosphere was expected, for example, through heating due to the sun. So essentially evaporating off particles into space. But the polar wind was different. You see, the particles in the polar wind were cold.
It's so cold, it's really cold.
So they couldn't have been heated by the sun. But they were traveling at supersonic speeds.
It was so fast.
The theorists came up with a hypothesis. This polar wind could be caused by an ambipolar field. The ambipolar field is a type of electric field that's created when positively and negatively charged particles move together within a plasma. In the Earth's case, the ambipolar field is generated by the movement of ions and electrons in the ionosphere. So the idea is that electrons are light, even the smallest kick in energy could send them shooting off into space. But on the other hand, ions, so the atoms or molecules that have lost their electrons, so have a net electrical charge, these will be much heavier, so they'll tend to fall towards the ground like anchors.
Anchor ahoy!
Now, if there was only gravity in our picture, after separating, electrons and ions would drift apart, right? But electrons and these ions have opposite charges, and we know that opposites attract, right? So this electric field works against some of the effects of gravity, preventing the charges from separating completely. It's kind of like a tug of war between gravity and electrical forces. Gravity pulls down the heavy ions, and the electric field pulls them back up. They reach a balance, and there they can stay bound together by their opposite charges. And this is why it's called ambipolar. It's bidirectional, working in both directions. Ions are dragging them down and electrons are pushing them up. This counterforce to gravity is essentially pushing the atmosphere up, so much so that some of the ions will escape into space, and more so at the polar regions where the magnetic field lines are open, allowing the plasma to escape more easily. The theorists figured that this field should start at about 250 kilometers in altitude, because this is where atoms in our atmosphere will break apart into negatively charged electrons and positively charged ions. But one problem: it was predicted to be incredibly weak. So up until now, we just haven't had the technology to measure it unambiguously. Now, NASA launched the Endurance rocket mission from the Arctic to see if they could prove that the ambipolar field actually exists once and for all. The key is to measure the subtle changes in the energy of electrons escaping from the ionosphere. The sun's helium-2 emission line at 30.4 nanometers causes photoionization. So an atom or molecule in the atmosphere that absorbs this photon will emit an electron, also known as a photoelectron. So the Endurance mission was equipped with a photoelectron spectrometer, PES, to observe the energy of these photoelectrons. As these photoelectrons travel upwards through the ambipolar field, they're slowed down, and this energy shift is directly proportional to the strength of the electric field. By carefully analysing this energy shift, scientists are able to quantify the ambipolar field, and they did it twice just for safe measure. Once whilst the rocket was going up, and once whilst the rocket was coming down. And this is what they saw. This graph shows the change in potential against altitude on the left for the way up and on the right for the way down. Now, from theory, if the ambipolar field is the only mechanism driving the electrostatic field of Earth, then the resulting electric potential drop across the exobase transition region would be as low as 0.4 volts. This region is the altitude range in the Earth's atmosphere, roughly between 250 and 770 kilometers. And it's where the atmosphere transitions from being collisionally bound, where particles will frequently collide, to collisionless, where they rarely collide. Anywhere above the exobase, ions are no longer held tightly by the neutral atmosphere and can readily escape into space. In this study, the electric potential drop in the exobase transition region was measured to be 0.55 volts, so well within the 0.4 volts required for the ambipolar field, being the only outflow mechanism for the dense cold plasmas seen in the magnetosphere. But also know it's tiny, about the strength of a watch battery.
So weak.
This is their plot of the ion density against altitude. The red line shows what you would expect if there was only gravity, and the black line shows what you would get with this ambipolar field. There's clearly a bigger density of ions up in the atmosphere thanks to the ambipolar field. About 3,800% more at the boundary, to be exact. The ambipolar field increases the atmosphere's height by 271%. So what's holding the atmosphere up? Well, without a doubt now, it's the Earth's ambipolar field. Now, many more questions arise out of this study, like what are the implications it has on Earth, our clouds, our thunder and lightning, and more importantly, life? And do similar ambipolar fields exist on other planets? Anyway, that's all I have time for this week. Thank you to my YouTube Perks members for supporting this video. If you enjoyed this video, please don't forget to leave me a like, share, and subscribe.
Floating through the cosmos, stars within my sight. With a rocket's hum, I'm on a cosmic flight.